Before we talk about how to find the general solution for any kind of system of linear equations with repeated or real eigenvalues, we're going to have this quick video, well, a quick video for me, a longer video for you if you're doing as you're told, but we're going to find out what does the general solution look like for the previous system. And we're going to use that as some kind of inspiration because, again, knowing how one example works does not mean all examples work that way, but a lot of times if we can analyze one thing, it gives us a starting point, thinking, well, maybe things might always look like this. Can we test that? What do we need? What are we going to require? What conditions must be satisfied? And that's exactly what we're going to do in this video and the next video. Solve this equation, because we know how to solve this equation, this system of equations. And then we're going to, in the next video, try to generalize it. And we will, with some stipulations. So what you're going to need for this video is you're going to need 2.4. 2.4 is where we solved decoupled systems. You're also going to need either 1.8 or 1.9. I recommend trying 1.8. Integrating factors is useful, but sometimes using the guessing method in 1.8 is really going to save you a lot of time. And I think it's what a lot of us are not as good at. So I would recommend trying to use this guessing method because it can really make things a lot faster if you have constant coefficients. And we're going to have a lot of constant coefficients in this chapter because we're looking at linear systems. Okay, so again, this is decoupled systems. You may need to review this, but I want you to pause the video and solve that system. Okay. Solve this system. It is partially decoupled. You're going to solve for y first, and then you're going to use y to solve for x. You'll have to use the method of undetermined coefficients or guessing, however you want to say it. So go ahead and pause the video now. Solve that system. Okay. What you should have gotten when you solve that system is that y of t is the vector, and there's multiple ways of writing this, and I'm going to actually rewrite it quite soon. But it should be something like k1 times t e to the negative 2t plus k2 e to the negative 2t. And the y value is always just k1 e to the negative 2t. We know the y value is going to look like that very easily because, right, dy dt is just negative 2 times y. That's our easiest differential equation to solve. And again, which one you called k1 and k2 doesn't really matter. When you use undetermined coefficients, you're going to guess this, but things are going to cancel out. And remember, that's when we add that t and see if that works. And then you will indeed get that. So this is what we have as our solution. This is our general solution to that system. And I'm going to rewrite this a little bit because I'm going to notice something. Let's say we're looking at an initial value problem. Right, if this were an initial value problem, then we would have an initial condition of like x naught and y naught. And this initial condition says very interesting things about k1 and k2. Because we notice that k1 will always just be the initial value of y. And then if we plug in t equals 0 here, this whole thing becomes 0. And this becomes 1. So k2 is actually, again, just the initial value for x. So then we could rewrite this system, or the solution, and we are indeed going to do this a lot in this section. We could rewrite the system as y naught times t plus x naught e to the 2t. And again, this is just going to be y naught e to the negative 2t. We could write it this way. We could write it in a different way, right? Again, you may be writing it in this format, e to the negative 2t, x naught, y naught, plus t, oh no, plus t e to the negative 2t times y naught and 0. This is how we traditionally write these sorts of solutions. We're going to get something very interesting here. And you might say, Jason, why would I write it like this instead of that first way? And my answer would be, why not? Anyway, seriously though, why would we do this? You're going to find out in the next video. For right now, I'm just going to say, trust me, wait and see. But in the next video, we're going to talk about why this might be a useful way of doing it. And again, this is very convenient that we have a vector right here that's just our initial condition. Now, you may be wondering whether these are eigenvectors. I have bad news about that. I have half good news about whether these are eigenvectors. You may be wondering some other things. You may be wondering, is there always a t here? Is it ever a t squared? What's this look like generally? Well, in the next video, we're going to say, can we assume things look kind of like this? Will it be a solution? So that'll be a fun little thing to discover. And that's pretty much it for this video. Hopefully you got some good practice solving equations like this. If you did not, then I do recommend looking back over 2.4 and 1.8. The book has a big warning. They're like, warning, if you don't know where this solution came from, go back. Go back and review. I'll say it a little more lighthearted than that, but also, yeah, it's important to have your foundation solid for this class. That's it for this video. The next video, we're going to take this step further and say, how can we use this to try to find a general solution always? Will it always look like this? What are we going to need? And that'll be fun.